Okay, so this is step support assignment number 13. It was this question on sketching graphs. Let's get straight into it. You're asked to sketch this graph here. When you're asked to sketch a graph, get some X's down, and then look out for some obvious things. The first things you can look out for are roots, if you can, y-intercept, which you almost always can, and you can almost always assess extreme values of x. I'll talk about that, what it means in a second. Now, the y-intercept is when x is 0, which is because you're not moving across, you're just on the y-axis. When x is 0, this is clearly 9, so that's going to be 9. The roots are okay for this one because you put in y as 0, because on the roots you're not moving up or down, you're on the x-axis. Put in y as 0, and this you could solve by doing a substitution. I think we learned that in assignment number 9, I'm not sure. But actually what I'm going to do is notice this is very similar to this, except the x's are slightly different. But this factorizes really nicely into that. So maybe this factorizes really nicely as well, and it turns out it does into this. X squared minus 3, x squared minus 3. And then, of course, you can just say x squared minus 3 is 0, or x squared minus 3 is 0, but that's the same. Add 3 to both sides, square root, and we get our two roots at plus root 3 and minus root 3. Now, what does this mean? Assess extreme values of x. What it means is, for like a really large value of x, like 1,000, roughly what's y? Now, the reason I use a large value is because if I put 1,000 into here to get like 1,000 to the power 4, these numbers are going to be, well, this number in particular is going to be quite big, but it's going to be nothing compared to 1,000 to the power 4. Like, this term is going to dominate the others. And so y is just going to be basically 1,000 to the 4, which is a big positive number. So when you use a big positive number, I'm going to get a big positive number out. So the graph is going to be over here somewhere. What about when I use a really big negative number, the other extreme? Well, notice when you use a power of 4, a negative to the power 4 is going to be a positive. So I'm just going to be in exactly the same case. This term will dominate. It's a positive term because a negative to the power 4 is positive. So I'm going to end up with another positive thing over here. So the graph goes from this end to this end. And it goes through these 3 points. I think we can get a pretty good idea of what the graph must look like. But just to make absolutely sure, let's find some turning points. There's one of my turning points. Find dy by dx and make it equal to 0 to find your turning points. Dy by dx is this. Make that 0 to find the turning point, so that's going to be 0. I factored out a 4x already. Now, of course, I can divide both sides by 4, and I end up with my turning points at x is 0, because that bracket has to be 0, or this bracket is 0, which we've already done before, plus or minus root 3. So it turns at x is 0, which happens to be there, and x is plus root 3 and x is minus root 3. So it's turning at all 3 of these points. It goes roughly over here and roughly over here, so it's going to end up looking like that. And if you put this into a cubometer, it makes it look much better, and it makes it look exactly like this. Excellent. Let n be the number of distinct real values for which this is true. Now notice how they've made this graph here equal to 0. So what they're actually asking us for is how many roots does this have? How many distinct real roots does this have? Okay, for different values of b, notice as well that this graph is basically the same as this graphic, except they've swapped out a 9 for a b. So this is the graph I've got so far with a 9, and they've given me a b. Now we need to think about, what does this b actually do? In other words, what does this 9 do? Well, this 9 tells us the y-intercept, which is good, but it does more than that. If you change this 9, all that will happen to the graph is it will move up or down. It will translate up or down. Like, if I change that to an 8, sure, the y-intercept will be 8, but it won't like squash the graph in any way. The entire graph will just move down a bit. And likewise, if this becomes a 10, the entire graph just shifts up a bit. So what this question is saying is, can I find different values of b that give me a different number of roots to this graph? When you translate this graph up and down, will the number of roots change, and can you tell me how they change? And we can do this in the computer, right? So here's the graph. It looks a bit different because I've stretched it out to make it fit on one screen, but it is the same graph. I've got my b here, which is currently 9, so that's the same as what I have here. It just looks a bit different. Now, what happens if I change b? What happens if I make b bigger? Well, we can see immediately, as soon as I make b bigger and the graph translates up, I end up with no roots. I have no values for which this graph is 0. It's all above the graph, above the line. So as soon as b is anything bigger than 9, I have no roots. So that answers the first part of the question, right? If b is bigger than 9, I have no roots. The graph translates up, I don't have any. So that's A. What about b? Can I find a number b such that there are 1 root? So the number of roots is n is 1. Can I find a place here where the number of roots is 1? Well, I don't think I can, actually. Like, looking at all this, sliding up and down, I don't think there's ever going to be a point where it's 1. And you can think about that in the sense that the graph is pretty symmetrical, or it is symmetrical. So it seems like a hard concept to have one root here for this graph. So we're not going to have a point where we're not going to have any roots. So we're not going to have a single root, sorry. We have no roots here. We're not going to have a point where we have a single root. Now, what about two roots? Part C, two roots. Well, we can actually see a version with two roots. When b was 9, we had two roots. Are there any other points where we have two roots? Well, we don't there, but let's slide it down. So there, when b is 9, there's our two roots. Is there another point? Well, actually, if we go down far enough to get rid of that hump there, we end up with two roots. And where's that point at? Well, it changed when b dropped below 0, right? When b is at 0, it has three roots, which we'll come to. But when b drops below 0, we then only have two. And if it keeps going down, it stays as 2, right? So we have two options for two roots. We have either b is 9, which is the case here, or b is less than 0, and we just have those two up here. Okay, what about three roots then? Now, it's tempting to say you can't do three roots because we couldn't do one root. So how are we going to do three? Well, we actually saw it 10 seconds ago. If b was 0, 1, 2, 3 roots. So b is 0 gives us three roots. So that's good. And what about four roots? Well, again, we've gone past that one, right? All of this, there's four roots, 1, 2, 3, 4. So what were those values at? Well, we started at b is 0, that was three roots. The moment we go above that, we get to four roots, 1, 2, 3, 4. And how long can we stay at four roots for? Well, it's until we go down to that original position where we have two roots again. So when b is between 0 and 9, that's when we have the four roots. Right? So between 0 and 9 is four roots. And the last thing you want to do before you move on from this, and I do just want to make sure that this applies properly. Sorry. There we are. The last thing you want to do before you move on from this is say, well, have I assessed every possible value of b? So here, for instance, I've assessed everything bigger than 9 and said there are no roots. Here I've said equal to 9. Here I've said less than 9 and bigger than 0. Here I've said equal to 0. Here I've said less than 0. So I think that covers every single number. Bigger than 9, equal to 9. Between 9 and 0, 0, and less than 0. That's everything. So I've covered everything here. So at least I've covered everything. Like it might be wrong, it's not, but at least I've covered everything. Okay, excellent. Part 2 then. For what values of a does this curve, which contains an a in it, have a point in which both this and this equals 0? Okay, so here's the thing they've given me. Let's find dy by dx. There it is. Let's find d2y by dx squared. There it is. Now, I'm trying to make these things 0. When I look at this, I'm nervous because this is a cubic, and I do not like trying to make cubics 0 and solving them. Solving cubics is hard, but when I look at this, I see a lovely quadratic, so I'm good with that. Let's make this 0 first. Divide both sides by 12, and I get x is plus or minus 1. So this thing is 0 when x is plus or minus 1. And that's good, because read the question again. I want this and this to be 0. So whatever values make this 0, those are the only ones I need to try here, because I need them to both be 0. So now I'm not worried about trying to solve a cubic, because I just need to test the values that I already have, because I need to make them both 0. So let's test these two values in here. Let's test minus 1 first. Well, in fact, sorry, I've misspoken, haven't I? I'm not testing. I'm just trying to find an a such that this is 0. But I only need the minus 1 and the positive 1. So let's use minus 1 first. 4 times minus 1 cubed is minus 4. Minus 12 times minus 1 is plus 12 plus a. And I get that a has to be 8. Sorry, it has to be minus 8 if this and this is 0 at the point x is minus 1. So this whole thing here has this and this be 0 if that's a minus 8, and the point where it is both 0 is at minus 1. And then for the other one, if x is positive 1, we put positive 1 into here, we get 4 minus 12 plus a, and a is 8. So again, this whole thing here has dy by dx and d2y by dx squared both equal to 0 if that's an 8, and it happens at x is positive 1. And those are the only times it ever happens. Okay, and b is irrelevant because when you differentiate, you get rid of the b term, right? So b doesn't matter. Let's go to here. For these values of a, find the number of distinct real values. Again, they're talking about distinct real values, but it equals 0. So what they mean is they're talking about how many roots does this have for different values of a and b. Now, we only have 2 values of a, 8 and minus 8. So let's deal with 8 first, which gives us this case where we've got an 8 in here. And what I'm going to do is I'm going to try and assess how many roots does this graph here have. Okay, so I'm just going to assess how many roots does that have. Well, first I'm going to differentiate it, which makes this. I can then differentiate it again, and this all looks familiar because this is so similar to the thing we just did. And then finally, what I can also do is I can say that because of this part A here, because A is 8, this whole thing, where A is 8, has dy by dx be 0 and d2y by dx be squared at 0 at 1. That was what I've just figured out before. So I can make all of these notes here. I've differentiated again, and I can make this note, which is what I just found out, that both of those things are 0 at x is 1 if A is 8, which it is. Okay, so I've got all that down. Now let's try and solve dy by dx. Let's try and find all of the stationary points, or all the turning points. Now, this is a cubic, and I've already said that I don't like solving cubics. However, I know one of the solutions of the cubic. I know at x is 1, dy by dx is 0, which means I can factor out from this an x minus 1. Because I know this is definitely 0 at x is 1, because I just found that in the previous question, which means I can factor that out, and I can leave behind a different quadratic. Now, notice I've already filled in some stuff about this. I know this must be 4, because x times 4x squared is 4x cubed. And I know this must be minus 8, because minus 1 times minus 8 is positive 8. And now I just have to figure out what the d is. You could do some polynomial division, or you could just notice, well, this doesn't have any x squared terms. Currently, if I expand this, I'm going to get minus 4x squared plus dx squared, which means d must be plus 4. So you can always skip out on some polynomial division if you want to, if you see cubics, because you can just kind of figure it out. Okay, well now I can clearly take out a factor of 4 from that bracket there, and that leaves me with this, which does factorize into that. So what this is saying here is this curve here has 3 stationary points, 1 again, and at minus 2. So it actually only has 2 stationary points because the 1 is repeated. So it has 2 stationary points at 1 and minus 2. So it has gradient 0 at 1 and minus 2. And what I can do now is I can figure out, well, where are those points for y? Like, where on the curve are they? I know that it has gradient 0 at 1 and minus 2, but where is the actual curve? Well, I just need to put 1 and minus 2 in here. So let's put 1 in first. 1 minus 6 plus 8 plus b. So the coordinates are 1, 3 plus b. 1 minus 6 is minus 5 plus 8 is 3, 3 plus b. And when you put in minus 2 to the 4 is positive 16. That's going to be a positive 4, so you take away 24, so you get minus 8. Or so you take away quite a bit, and you get b minus 24. Just test that for yourself, but I think that's what you get. So I know that now that the graph goes through these 2 points. I know it goes through those 2 points, and I know it's stationary. It has gradient 0 at them. So now I can start making some progress, right? So let's get out a pair of axes. I know that the y-intercept is at b. That's always the nicest thing to do. And I know a few more things, right? Ignore these crosses for now. I'll talk about them in a second. I know that it goes through 1b plus 3 or 3 plus b, depending, it doesn't matter how you say it. And I know it's stationary here. So its gradient is 0 there. I also know that it goes through minus 2, b minus 24. And again, I know its gradient is stationary there. Now, what these x's represent, you might have figured it out, is when x is really, really big, this term dominates, and you get a really big number. When x is really, really big and negative, this term is positive and still dominates, so you get a really big number. So I know my graph goes through all of these kind of areas. It definitely goes through these points, and then it ends up over here and ends up over here. I also know that it turns here and turns here. Okay, now it might be easier for us to figure out, well, how is this a turning point if it has to go from here to here, right? If it turns this way, then it just heads up again. If it turns from here downwards, it just goes downwards again. And that's because this isn't a maximum or minimum. It is a turning point, but it's not a maximum or minimum. And we knew that because we know d2y by dx squared is 0 here at x is 1. which means this is a point of inflection. So it goes down, inflects, has a gradient of 0 momentarily, and then keeps going down. So our graph looks roughly like this. So this is a true turning point because it has to get it back up to B here. But this is just a flat inflection. So it just thinks about turning around, but then changes its mind and goes back up again. Right? And if you put this in a computer, it ends up being this. Okay, so that's my beautiful sketch done by a computer of this graph here where A is 8. And this intercept is here is B. This point, this turning point or inflection, I should say, is 1B plus 3. So right now you can see B is probably about 4 that I put in my computer, probably. And now I need to say, how many roots does this have for different values of B? So this is similar to what we did in the first part. So let's think about how many roots this has for different values of B. Now again, all B does is shift this graph up and down. So let's shift it all the way up to start with. Let's move it really, really high. This is what I've just been saying. Let's move it really, really high so that this minimum point here is above the x-axis. Well, how many roots do we have now? Well, 0, clearly. So I've shifted this graph. I've made B like 25, as you can see. I've shifted it up, and I've got no roots. So when do I have no roots? Well, it's when this coordinate here, the y-coordinate of this point, it's when that is bigger than 0. So it's when B minus 4 is bigger than 0. And if that is bigger than 0, I have no roots. It doesn't touch the line. Now, of course, I can rearrange that and say if B is bigger than 24, I have no roots. And I put it in red because it's important. I'll leave it there. Now, what happens if I shift this graph down just a tad until it looks like this? How many roots is this? Well, it's 1, clearly. It just touches this line and then goes back again. So it's 1 distinct root. When does this happen? Well, notice that this is again the y-coordinate at this point, and that's 0 now, isn't it? It's on the axis, so it's 0. So I need B minus 24 to be 0, and then I get 1 root. That, of course, means that B has to be 24. So if B is greater than 24, I have no roots. If B is 24, I have 1 distinct root. What about the next case? Well, I can move this down further, and I end up with a case that looks a bit like this. So I've just moved this down a little bit further, so this point here has gone down to here. How many roots do I have now? Well, I have 2, clearly. And now 2 things are going on to get this case. Both this coordinate, the y-coordinate of this inflection point, that's bigger than 0. That's above the axis. And this coordinate is below the axis. That's less than 0. So I have these 2 things going on, and that gives me 2 roots. Well, I can solve this, right? I can take away 3 from both sides, and I can add 24 to both sides, and I get, if both B is greater than minus 3 and B is less than 24, I get 2 roots. But I can combine those, right? B greater than minus 3 and B less than 24, 2 roots. So I can combine those things just into one statement. So that's what I've done. Excellent, so that's my third condition. What about if I move this graph down further such that this inflection hits the line? Just like that. Well, actually, I still only have 2 roots here. So I still have 2 roots when B plus 3 is 0. When the y-coordinate of this point is 0, I still have 2 roots. Of course, I can solve this. So when B is minus 3, I have 2 roots. And lastly, what happens when I move this down further? I end up with a case that looks like this. And again, I have 2 roots. So when B plus 3 is less than 0, I have 2 roots. And I can solve this, of course. B is less than minus 3. Now, look at the last 3 statements I came up with. I said B between minus 3 and 24 is 2 roots. Then I said if B is minus 3, I have 2 roots. Then I said if B is less than minus 3, I have 2 roots. But look at this. This is all just the same thing, right? B between minus 3 and 24, 2 roots. If B is minus 3, I have 2 roots. So I could combine those and just put a little or equal to sign there, because that's still 2 roots. But then I'm saying, even if I go beyond minus 3, I still have 2 roots. So I combine all of those 3 into just saying, if B is less than 24, I have 2 roots. And again, just quickly check, have I assessed every value of B? Well, if B is greater than 24, if B is equal to 24, if B is less, I think that covers everything. And those are my answers. Excellent. So what about for the value of minus 8? So I've changed the graph now. I've said I've put a minus 8 in instead of my positive 8 that I was working with before. Now, what you could do here is you could do exactly what I just did. Again, just with the minus 8. Exactly as I did it. Just change the numbers slightly to compensate for this negative, and everything will be fine. However, I'm not going to do it like that, partly because that would be boring, I've just done it, but also because there is a quick way of doing this, which is to notice, well, let's call this blue one f of x just for now. So the blue one that we just dealt with the plus 8, let's call that f of x. And now let's figure out what f of minus x is. Well, that's just when I put in an input of minus x instead of x. So I'm going to put in minus x every time I see it, and this minus x just changes that sign. But minus x to the 4 is positive x to the 4. And minus x all squared is positive x squared. So I end up with this graph here, which is what I was just about to embark on doing. So therefore, the original graph reflected in the y-axis is our new graph, because this is just a reflection in the y-axis. So our original graph that we just did, reflected in the y-axis, is our new graph. But what happens when we reflect a graph that looks like this in the y-axis? Well, we just get a graph that looks like this, and the number of roots does not change. And the cases don't change either. It's just the same question, right? It doesn't matter whether the graph has been reflected like this. So whatever values that we had for b here, they're going to be the same here. And we don't have to do the whole thing again. Really well done if you spotted that, because that was a difficult spot. Also really well done if you just did the whole thing again, because doing the whole thing again is good maths. Anyway, the last part of the question, sketch this curve in the case where a is bigger than 8. Now, this is tough, and we're going to have to employ a new tactic. And my new tactic is, well, let's just find dy by dx. Now that gives me this cubic, I believe. And what I'm going to do is I'm just going to abandon all hope of trying to sketch this for now. I'm just going to try and sketch this. I'm going to call this graph g of x, and I'm going to try and sketch g of x, which is the derivative of the thing that I actually want to sketch. But hopefully you'll see why I'm trying to sketch this in just a moment. So let's try and sketch this graph here. Well, I know it goes through the point A, if I'm sketching this here, and I also know it's a cubic. Now, cubics don't look the same as quartics. They don't go from here to here. Cubics, positive cubics, go from over here to down here, because when x is massive and positive, this term dominates for a big positive. When x is massive and negative, this term dominates for a massive negative. So I know it goes through kind of these two areas of the graph, and it goes through A. So that's good. This is taking shape, the sketch. Okay, now let's find g dashed of x. So let's do the derivative of the thing I'm sketching to find the gradient, of course, or to find the turning points, I should say. When I differentiate that, I get this. And now let's set that to be 0. So stationary points of g are when the derivative is 0. And I think we divide this by 12, and then we find x is 1 or minus 1. So this graph is stationary. Remember, this graph is not the one I want. It's this one for now. This graph is stationary at 1 and minus 1. All right? Well, let's find out where the graph actually is at 1 and minus 1. Well, at 1, my graph is 4 times 1 cubed, which is 4, minus 12, plus a, which is 8a minus 8. So at the point 1, I know a few things now. I know it's a stationary point, and I know that the y-coordinate is a minus 8. Now, this is good because it says a is bigger than 8. So I know that this point here is above the x-axis, because a, the smallest a can be, is just over 8, which means this point is always going to be just above the line, minimum. So this is up here. What about when x is minus 1? Well, and also I should say, yeah, it's a stationary point, so it goes through there flat. What about x is minus 1 then? Well, g of minus 1 is minus 4, because that's a minus 1 there, plus 12 plus a, which gives me a plus 8. So I know that this point here at minus 1 has a y-coordinate of a plus 8, and I also know that that's a stationary point. And so this cubic hasn't turned out to be too hard to sketch, because I know it starts over here, ends over here, and goes through these 3 points, and the only places where it's flat are here and here. Pretty self-explanatory to sketch that just like so. All right? So that's my sketch of this function. Now, of course, that's not what the question asked me to do. The question asked me to sketch this function. But here's how this helps. Like, you're probably wondering, why have I bothered to do that? Well, let's look at this function again. The only root, this function only has one root, and it's right there. It only ever has one root because, as I discussed, this point here is always above the x-axis if a is bigger than 8. So this graph, no matter what you want to do to it, has one root. And it never has 0 because, of course, this point is down here, this one's up here, so it's got to cross somewhere, and it's got to do it over here. So my function that I just sketched only has one root. It's only 0 one time around here. But the thing that I just sketched is the derivative, right? Which means the derivative of this function is only 0 once, just like g of x is, because they're the same. So the derivative is only 0 once, and even better than that, I know where it is. It's 0 there, roughly. It's 0 there. The derivative of this function is only 0 once, and it's around this area of the graph. It's when x is beyond -1 at some point. So it's when x is less than -1. So just to repeat that, g of x only has one root. It can only have one root because of this thing, which means it's only 0 once. That's what the root is, which means the derivative of the thing I want to sketch is only 0 once. And it happens when x is just less than -1, or a bit less than -1, somewhere over here. So let's get back to this sketch then, and let's talk about what that means. It means that this graph only has one stationary point, right? If its dy by dx is only 0 once, it only has one stationary point, and even better, I know that happens when x is less than -1, somewhere around here. And now I think I have everything I need to sketch this, because let's put some axes down. I know this goes through 0, 0, because there's no constant at the end. So it goes through 0, 0. It's a quartic, which means it's massive up here and massive over here, just like we've seen before. And now, I know it only has one stationary point. There's lots of things I could do with one stationary point here, like I could just put a U shape through these, or whatever. And this is where the key point comes in, which is, I know that stationary point happens somewhere over here. Like beyond x is -1. It happens somewhere over here. So what I need to draw a curve that goes through this point and these two kind of areas over here. And it's only allowed to turn once, and it has to do it somewhere on this line, roughly. Right? And you can, mull this over, but I think the only thing that you're going to be able to come up with is something that looks a bit like this. Right? It curves down here, and then it never turns again. Now, I've put a little flick into it here, and you might be wondering, why have you done that? Well, it's because we've seen some kind of quartics before, and they tend to have this flick here. Now, this quartic had a flat flick. It had an inflection point, remember, from part 2? This one doesn't. This isn't flat at any point. It just kind of has a sort of it thinks about becoming flat, and then it doesn't. It just goes back up again. So this isn't a turning point. I've just flicked it because quartics generally have those little flicks in them. And of course, I can put this in a computer, and I end up with this sketch here. So it does have that flick. It's not flat at any point, but it does have the flick. It's only flat down here. Turned out to be a bit beyond -2. Went through there, and it ended up, of course, higher over there and higher over there. And that's my sketch. Really well done if you stuck with me through that.